All right, listener name. Let's dive into some calculus today with this deep dive. You submitted some audio lectures and notes, and looks like you're wrestling with implicit differentiation, inverse functions, and their derivatives.
Yeah, those can be tricky. A lot of people learn the steps, but they don't always get to the why they're so powerful.
Yeah, for sure.
Like, take implicit differentiation. It's like having X-ray vision for relationships in math.
Okay, I like that. X-ray vision, I'm listening. But before we put on the special glasses or whatever, can we back up a bit?
Sure.
What exactly is an implicit function? Because it seemed kind of vague in the lectures.
Okay. So think of it this way. An implicit function, it's like trying to describe, like, the shape of a roller coaster loop.
Okay.
But you're not allowed to give a simple equation for, like, the height as a function of distance.
So I know it's there. I can see it,
Yeah.
but I don't have the equation.
Exactly. You just know the loop exists.
Okay.
You can see its shape.
Right.
But you don't have that clean y== formula.
It's like we know X and U are connected somehow, but it's hidden, not just given to us directly. Is that right?
Exactly. You got it. That's a great way to put it. And that's exactly where implicit differentiation, that's where it comes in.
Yeah.
It lets us find the slope of a tangent line to that roller coaster loop, even if we don't know that exact height equation that you're talking about.
Oh, okay. That's cool. But I still don't quite get how we actually do that. In practice, I mean.
All right, so let's look at an example. Let's use one from your notes, finding the slope of the tangent to the curve. It's y6x equals 3 at the point -2, 3.
Oh, yeah, right. That one. That one really threw me for a loop.
The loop. I see what you did there.
It's true. It's true. But I could picture the point on the graph. But finding the slope there without solving for y first seemed impossible.
Uh-huh. And that's the beauty of implicit differentiation. We don't need to solve for u explicitly. Instead, we differentiate both sides of the equation, just as it is treating y as like an unknown function of x.
Wait a second. Slow down. How can we differentiate y if we don't know how it relates to x?
Good question. And that is precisely where the chain rule comes in.
Ah, the chain rule. Okay.
Yeah. What we're essentially saying is, hey, we know that u might change with x, right?
Okay.
Even if we don't have that exact formula. So when we differentiate any term with a y in it, we have to multiply by digs.
Right, to account for that.
Exactly, account for that potential change.
So did x is more than just a symbol.
Right.
It's telling us something real, like how much u changes when x changes just a little, right? Like the speed of u compared to x, or am I getting that right?
Precisely. Exactly.
Yeah.
That's a great way to think about it. It's that relationship between the change in y with respect to x.
Okay. Okay, now I'm starting to see it. So back to that roller coaster. Dead x would be like figuring out how steep the track is at any point, even if we don't have that nice height formula.
That's a perfect analogy. And that's incredibly useful, think about it, in engineering and physics.
Where you don't always get those neat formulas.
Exactly. You often encounter these relationships. They're super complicated. Sometimes it's impossible to express them simply, just with a simple formula.
Yeah.
But implicit differentiation swoops in and it's like, nope, doesn't matter. We can analyze these relationships without solving for one variable in terms of the other.
Wow. So it's really breaking down some walls here, huh?
Yeah.
No longer limited by needing a y= equation.
Exactly. It's like finding these hidden connections.
I like it. Uncovering those secret relationships. That's implicit differentiation.
That's it. You got it.
All right, that's cool. I'm definitely feeling more clear on that now.
Awesome.
So where do we go from here?
Yeah, it's a great tool to have in your calculus toolbox. And it leads us really well into our next topic, which is inverse functions and their derivatives.
Yeah.
You might think at first that these ideas are totally separate, right?
Yeah, it's not immediately obvious for sure.
But remember how we were just talking about like implicit differentiation and how it lets us see these hidden relationships?
Mm-hmm.
Inverse functions and their derivative, they have like their own special connection too. It's almost like a mirror image or something.
Intriguing. I'm intrigued. But before we get too far, can we just back up for a second?
Sure.
Just the idea of inverse functions in general.
Mm-hmm.
Flipping a graph over the line, y-x, I can kind of get it visually.
Yeah.
But when it comes to actually finding those inverses
Yeah.
and why we even care, I always get tripped up.
Yeah, you've hit on a really important point there, which is it's not just about like flipping the picture, right?
Right.
It's about understanding what that flip really means mathematically. So imagine a function as like a machine, right?
Okay.
So you put an x and it spits out y.
Right, like a little input-output.
Exactly. Now the inverse function, it's like hitting the undo button on that machine.
Okay,
Right.
so if I take that output y and I put it into the inverse function,
Yep.
boom, I should get my original x back.
You got it. But, and here's where things get a little tricky. This is where those restrictions come in.
Right, right.
Not all functions, they don't all have inverses that, that behave how we want them to.
You can't all be reversed so easily.
Exactly. Exactly. Like, for example, think about if you tried to, like, unmix ingredients
Oh, okay, yeah.
after you've already baked a cake. You see what I'm saying?
Yeah, it's not going to happen.
Exactly.
Yeah.
Some things you just can't perfectly undo. And so in the same way, for a function to have like a well-defined inverse, it has to be what we call one-to-one.
One-to-one, right.
Meaning that each input, each x, it maps to one and only one unique output, or y.
Makes sense. So each input has its own special output, no sharing allowed.
Exactly. Exactly. And your notes focus specifically on arcsine and arcosine,
Right.
which are the inverse functions of sine and cosine, right?
Right.
But sine and cosine, they're kind of mischievous.
Yeah, they are.
Because if you let them, they'll just keep repeating their values forever. They're
Yeah.
periodic, right?
Right, those wavy graphs just go on and on.
Exactly. They just keep going and going.
Yeah. So we got to like put them in a box or something, restrict them
Exactly.
to make them behave.
Exactly. We restrict their domains to make sure that, at least for a little bit, they're behaving and they're one-to-one.
Okay.
So we take just like a little snippet of those sine and cosine graphs where they are one-to-one.
Okay, so we're choosing our battles here.
Exactly.
They're finding the well-behaved part.
Exactly. And then we're allowed to do our flip over that line, y or x, to get our arcsine and our arcosine.
Okay, yeah, that makes sense.
Mm.
But how do we actually find the derivatives of these inverse trig functions? The formulas in the lecture just seemed kind of like poof.
Magic.
And this is where things come full circle, and it all ties together so beautifully.
Yeah.
Because, believe it or not, we actually use implicit differentiation to find those formulas.
Wait, really?
It's like a secret passageway.
Okay, so it's not just for those curves. It can do inverse functions, too.
It can, absolutely.
Yeah.
So let's say we have y equals our Garak is x.
Now, that also means that sine of y equals x, right? We're just using that inverse relationship.
Right, so it's like a round trip.
Exactly.
I go one way with arcsine, come back with sine.
You got it. So we plug x into arcsine, we get the y, plug y back into sine, boom, we get our x back.
Back where we started.
Back where we started. Now, here's where the magic happens. Are you ready?
Okay.
We can differentiate both sides of that equation, that sin e equals x. We differentiate both sides with respect to x.
Okay.
And this is where implicit differentiation comes in.
Okay.
We get cos e times dx equals 1.
Okay, keeping up.
And then we can just solve for dx, and just like that, we have the derivative of arcsine.
Wow, okay. That's cool, but we still have a y in our derivative, right?
Ah, good point. Good point.
How do we get rid of that?
Remember those trig identities? They always seem kind of like magic spells to me, you
A
know?
little bit, yeah.
Just like appear out of nowhere.
Yeah.
But this is where they really get to work their magic. So we can use, for example, the Pythagorean identity, sin y plus cos y equals 1. And we can use that to rewrite cosy in terms of x, and boom, no more y in our derivative.
It's like we used implicit differentiation, inverse relationships, and trig identities all to get to those derivative formulas.
It's like a puzzle. You got to use all the pieces.
Exactly.
You got it. And the best part, the same idea applies to finding the derivative of arcosine.
Oh, fantastic.
We start with cosy, we differentiate, use that chain rule, and then a little sprinkle of magic, we substitute with a trigonometric identity to get everything in terms of x.
Wow, we're like mathematical detectives, except instead of a magnifying glass, we've got implicit differentiation.
Exactly. You're uncovering those hidden patterns.
I like it. So are we done once we have those formulas, or are there like more layers to this onion?
Oh, there are always more layers. Having the formulas is just the beginning. It's like having all the pieces of a puzzle, but now we need to figure out how they fit together.
All right, we got to put those pieces together, make sense of it all. So where do we even begin? We've got implicit differentiation, inverse functions, and their derivatives. It feels like a lot.
It's about seeing the bigger picture. Remember our roller coaster loop? We used implicit differentiation to find the tangent line's slope at a certain point. But what if we want to know how that slope changes?
We'd need the second derivative, right? Like, is the curve bending upwards or downwards?
Exactly. And this is where those inverse trig derivatives come in. They might have seemed like a side quest, but they're about to become super relevant.
Not seeing the connection yet. How does the second derivative of an implicit function have anything to do with inverse trig functions? They seem pretty different.
Okay, so let's go back to our example, that curve, y6x or t equals 3. When we found did x, it wasn't a simple x expression, right? There was still some z's hanging around in there.
Right, because we couldn't just solve for u directly.
Exactly. So to find the second derivative, we have to differentiate that did x expression, which means differentiating your again. And that, my friend, is where those inverse trig functions come in.
Okay, now you've got my attention.
In this case, when we differentiate did x, the derivative of arcsine pops up, like a little surprise guest star.
Whoa, for real. So we're like using implicit differentiation within implicit differentiation, and the inverse trig derivatives are essential for that.
Exactly. It's all connected. And this isn't just some mathematical magic trick. This understanding helps us analyze complex systems in physics, engineering, economics. It's everywhere.
Wow, okay, so we've gone from implicit differentiation to inverse functions, and now we're seeing how it's applied in all these different fields.
It's about understanding change in all its forms.
I like it. Speaking of change, there was that problem with parametric equations. Remember that one? In the source material.
Ah, yes. Parametric equations. They're fascinating because they bring in this idea of a third variable, often representing time, which controls both x and y.
Right, like plotting the course of something moving along a path.
Yeah.
But how do we even start with derivatives in that situation?
It's elegant, actually. To find did x, the tangent line's slope at any point, we just divide dit by dx dt. We're looking at how yaw changes with time and x changes with time, and then comparing those rates.
Yo, that's so clever. So we can find the second derivative the same way, right? Just differentiate again.
You got it. Differentiate did x with respect to x again, using the chain rule and those same parametric derivatives. It might look messy at first, but it's the same principle at work.
This is amazing. We've gone from implicit differentiation to inverse functions and now to parametric equations. Who knew it was all so connected?
That's the beauty of math, isn't it? These concepts might seem separate at first, but they're all threads in the same tapestry. As you keep learning, you'll see these connections again and again.
This deep dive has been incredible. I feel like I finally have a handle on implicit differentiation, inverse functions, and their derivatives. Thank you for guiding me through this.
And remember that roller coaster we talked about, all those loops and twists?
Yeah.
Well, understanding these calculus concepts is how engineers actually design those curves. They make sure the ride is thrilling, but also safe.
Wow, that's a perfect way to bring it all together. Calculus isn't just abstract equations. It's the language that helps us understand and shape the world.
Exactly.
I can't wait to see where these new tools take me next. Thank you so much for this deep dive, listener name. This has been great. Until next time.